So, good afternoon, everybody. It's my pleasure to introduce Yinon Spinka from Vancouver, who's going to talk about A Tale of Two Balloons. Yinon?
Okay. Thank you, Marcelo. Yes, it's a pleasure to be here. Here being Vancouver and Brazil at the same time, IMPA. I guess that's one of the nice things about this this period in time. I don't know if I would have been able to come otherwise. So thanks for having me. So I'm going to tell you about a problem that I've been working on with Omer Angel and Gourab. It's called The Tale of Two Balloons. And this alludes to, the title alludes to two different things. One may be kind of similar to A Tale of Two Cities, but also in Israel, there's a children's book called The Tale of Five Balloons. It's a well-known children's book where these balloons eventually popped. And that's also part of the story here. And before I tell you what this process is, maybe I'll just mention this was motivated by some questions of Itai Binyamini relating to coalescing random walks and annihilating random walks, where some results were obtained there, and it's not clear how analogous these things are, but that was part of the motivation. All right, so let me begin, and let me first just describe to you what this process is. You see here some pictures, which I'll explain a bit later. So we call this the balloon process. So in general, you have some metric space, omega rho, and you're given some initial set of points, which we'll call pi here. So these are depicted here in the picture below, say these 6 points, which are our initial points. And what we do in this process is we start growing balls around the points, centers around these points. These are our balloons. And we grow these at rate 1. Everywhere they always grow at rate 1. Okay, so perhaps after a small time, these are our balloons. Okay, so this is what the process looks like after a short amount of time. And as time increases, the balloons continue to grow just at rate 1. So they all have the same radius, which is just the time. So at time t, they all have radius t. And eventually, there's no way to avoid this. Eventually, two balloons will collide. And whenever two balloons collide, they're just erased. Okay, so they just pop with each other. They hit each other, they pop, and they just disappear completely. Okay, so at this point in time, these disappear. Okay, and then we just continue. So a bit more time passes by, all the balloons grow, and eventually these two are going to collide and disappear. Okay, and we're just going to be left with these two, and then they'll continue to grow and grow and grow until they hit each other and collide. Of course, there might be points out of the screen which we don't see, which start to come into and from other places, and then those two collide with each other and so forth. Okay, so I should also say that if you have any questions, please feel free to stop me. You can just interrupt and ask. If you prefer, you can write in the chat. If I don't notice, then Marcelo will stop me and tell me. Okay, so I hope this process is clear. Let me maybe show you a simulation. Maybe that will help a bit. Okay, so here's a simulation in the Euclidean plane, two-dimensional plane. Okay, so I don't know if you can see here. There's very, very bright points. These are the initial points, but that's okay. As they grow, you'll see them. Okay, so I'll hit play here. And then you see these start to grow, and as two hit each other, they pop and disappear, and the popped ones here are shown in gray, just so that you can see what happened before. So the blue balloons are the ones that are still active. Okay, and at some point in time, for the simulation, we're kind of going to change scales. So at this point in time, I stop the simulation, and I'll rerun.
We have a question from Milton Hara.
Yeah.
If it's clear that this process even exists.
Okay. It's not immediate. I'll say a word about this shortly. Okay, I'll delay that a bit, and I'll come back to that. Thank you. I should have mentioned this. So you need some assumptions on the initial point process, but in all the examples and cases that we'll consider today, these are satisfied and the process exists. Yeah, but this is a good point. Okay, so at some point in time here, what I'm going to do is first I'm going to stop depicting these gray inactive balloons, and I'm also going to change time frame at like the scale. I'm going to move to an exponential scale, and instead of so I'm kind of zooming out, and then at an exponential scale, so it appears that all the balloons have the same, that the radius isn't changing, but this is just because we're zooming out to see more and more balloons, and that's why it looked like they were coming in. And this is a nice surprise at the end. Oh, this I don't want to show you yet. I'll come back to this. Okay, so I hope that helps understand what the process is, if not why it's well defined, but at least what exactly the process is. Okay, so any questions about how the process is defined? Okay. So today in the talk today, I'm going to consider a few different scenarios. So our metric space will be either Euclidean space in any dimension. In fact, even in dimension 1, the problem is not trivial. And I should mention that there's an ongoing work of Liggett, I think Holroyd and one of their students on this problem in 1 dimension. So even there, it's non-trivial. So we'll look at Euclidean space. We'll look at the hyperbolic plane in the Poincare disk model with any constant curvature. So the process does depend on the curvature. At least there's no a priori reason not to expect dependence on the curvature. Whereas in Euclidean space we have scale invariance, right? So if we scale space, it's just the same as changing the intensity of the Poisson process and the time and some time scale. Okay, we'll also look at regular trees. So a tree or any graph for that matter, if we think of the metric space as the vertices themselves with the discrete metric, then the process isn't going to be well defined, because we're going to have, at half integer times and at integer times, things are going to be certain ties. Like many balloons will meet each other simultaneously, and we'll need to break ties and things like this. So we're going to view this as a continuous metric space, just by thinking of every edge as identifying it with the unit interval. And then the points are actually going to lie on the edges themselves. And our initial point process is always, in all of these cases, we're just going to consider a Poisson point process. So I hope everyone is familiar with this, but I'll just say quickly, this means that in any region of space, the number of points is distributed as a Poisson random variable, whose mean is the volume of that region. And disjoint regions, the number of points there are independent. Okay, so we already saw the example of the Euclidean plane. All right, so the main question of interest here is whether this process is recurrent or transient in the following sense. Okay, so we'll say that it's recurrent if almost surely every point of the space is visited infinitely often. Okay, and by infinitely often, I mean actually an unbounded set of times. Okay, so if I look at a particular point in space, and I look at the times at which it's covered by some balloon, I want that set of times to be unbounded. Okay, so balloons return to every point infinitely often. That's recurrence, and transience means that almost surely every point is visited finitely often. And again, it's not a priori clear that this process is either recurrent or transient. Maybe it's neither, right? Maybe this event has probability, has a non-trivial probability. Maybe it depends on the point you're looking at and things like this. So we want this almost surely for all points. All right, so here's our main result. So the main result is that in RD, in any dimension, this process is recurrent, whereas in the hyperbolic plane and regular tree with any degree and any curvature for the hyperbolic plane, this is transient. Okay, so already let me mention that, if you look at the case of RD, for example, this is already telling us that the recurrence here is not related to recurrence and transience of a simple random walk, for example. This is in all dimensions always recurrent. And I don't know if it was clear from the simulation I showed you that this was recurrent. We can go back and look at that quickly. So what we're kind of looking for here is the gray area, right? That's the area that balloons visited at some point. There's still a lot of white space, and maybe it's not clear, and you want the balloons to return infinitely often, not just once. But maybe in this exponential time scale, maybe it's a bit clear that the balloons are kind of all around. It's not obvious. So let me also show you now the hyperbolic case. Sorry, let me stop this and go from the beginning. Okay, so we again have an initial set of points. This is already at some time epsilon. That's why they have some area. And remember, all balloons have the same radius, but this is hyperbolic radius, right? So they appear, their Euclidean radius is not the same everywhere. But the hyperbolic radius at time t, they all have radius t. And as to hit each other, they pop. And here, you look at this a bit, and you see that as time passes, the active balloons kind of look like they're around the boundary. From time to time, some balloon grows and starts coming close to the boundary, but it's not really going to make it. At some point, it's popped. And now there's like a good 5 seconds where you don't see any balloons that come close to the origin in the Euclidean sense, at least. Like they look very close to the boundary. So again, it's not so obvious from the simulation, but the theorem tells us that this is indeed transient.
Milton has yet another question. Milton, maybe you want to unmute yourself.
Yes, so I just was wondering if it's this dichotomy between recurrence and transience was related to exponential volume growth of these spaces.
So I'll talk a bit about the proofs, and maybe you can judge for yourself. We don't know exactly what the conjecture is. We don't have a result that that can say something like and answer a question like that. But to me, it seems like it is the exponential growth. You might imagine maybe it's amenability or non-amenability, but it does look more like the exponential growth. But I don't have a strong enough conviction to actually say that I believe that it's exactly that. I have a feeling that exponential growth would be transient and maybe polynomial growth will be recurrent, but in between, I'm not sure if there are some other examples.
There is another question from Shanji. How does the negative curvature help for transience? Yeah, so again, we'll see a bit in the proof, but it's not so much that it doesn't seem like it's so much the negative curvature itself and more the exponential growth.
That's what it looks like. Okay. Right, so this is the basic result, transients versus recurrence. But actually, our proof methods will give a bit more information. So for this, let me give you a definition which we'll need throughout the entire talk. So let's let pi sub t denote the point process of the balloons, of the centers of the balloons which are active at time t. Okay, so pi 0 was just our initial point process pi. And as time goes on, some of these points are deleted, and this process is just a decreasing set in t. Okay, the points active at time t. Right, so at time t, we have some active centers. They all of these are balls of radius t, and we let r sub t denote the distance to the nearest center of a balloon. Okay, in other words, the origin is covered by a balloon at time t, if and only if RT is less or equal than t. Okay, that means that the origin is covered at time t, and therefore the origin will be covered infinitely often. What we need for that is that the limit of RT minus t is less or equal than 0, more or less. Right, it could be, I mean, if it's 0, okay, if it's 0, that's like a critical thing, but definitely if it's less than 0, then it's recurrent for the origin. But if we really want it to be recurrent at every point, we would need here that it's minus infinity, almost surely. If you think about it a bit, that would tell you it's recurrent everywhere. And if it's plus infinity, that would tell you that it's transient everywhere. So this limit of RT minus t is what's important. And actually our results tell us something a bit more. Tell us about the limit of RT over t. Okay, so the critical point for this limit is when it's 1. That's when it's kind of, you can't decide if it's recurrent or transient just from this. But actually in RD, this limit is always 0. In particular, it's recurrent. And in the hyperbolic plane and the tree, it's strictly greater than 1, in particular transient. In the tree, actually, we know that it's exactly 2. And in the hyperbolic plane, we have some lower bound on it, which is given by this expression, which is roughly 1.44. Okay, so these are the results that I'm going to talk about today. Before I get into the proofs, let me give you a bit of background, including answering the question of whether this process is well defined. So indeed, for the process to be well defined, we need some assumptions in pi, and it's enough that that pi satisfies these 3 assumptions here, which okay, I won't give it a name, but these will be our only assumptions here. So the initial point process is discrete. There are no 2 pairs of points which are equal distance. Okay, and you can kind of imagine why that's important. If you have 2 points and 2 other points at equal distance, maybe one of those points is a shared point. And as the balloons grow, we're going to have this simultaneous collision, and then we have to break ties somehow. Okay, so in order not to be in that situation, we want this assumption. And finally, the last assumption is that there's no infinite descending chain. What this means, an infinite descending chain here is a sequence of points such that the consecutive distances are decreasing. Okay, so something that looks like this. Okay, and you can imagine why this would be a problem, because when you kind of think ask yourself, is this balloon going to pop with this balloon? Well, it depends whether this balloon popped with this balloon first or not. And that, in order to answer that, you have to know whether this balloon previously popped with this balloon and so forth. And you're going to like get into an infinite kind of recursion, which you're not going to get out of, and it might not be well defined. But under these 3 assumptions, deterministically, right? Any deterministic set of points which satisfies these three assumptions, the process is going to be well defined. Yeah, so maybe I didn't stress this before. Let me say this, let me just stress this now. The only randomness in the balloon process is in the initial set of points. In the Poisson point process that of the points you start with, once you choose those points, everything evolves deterministically. And the fact that the Poisson point process satisfies these three properties, at least for RD, this was shown by Hegstrom and Meester, but the same types of ideas, which are not too difficult, go through for all of these examples I'm talking about today, and for other kind of reasonable spaces. Okay, another important thing here in the background is the relation to stable matchings. So stable matchings, perhaps some of you have heard of this. This is something that in the 60s was studied by Gale and Shapley. So in the classical setting, you have n men and n women, and you'd like to match them to each other to create like a perfect matching where every man is matched to a woman and vice versa. And we assume that every man has a ranking, has a preference order on the set of women, and every woman has a preference order on the set of men. And matching is called, well, we want to say what it means to be stable. Let me define what it means to be unstable. A matching is unstable if there exists some man and woman, okay, perhaps this man and this woman, which are not matched currently. So they're not partnered in this matching. However, each of them prefers the other over their current partner. So this man prefers this woman over the woman he's matched with, and this woman prefers this man over the man she's matched with. And presumably in this situation, these two would just divorce their partners and marry each other, right? And that's what makes this matching unstable, that there are pairs that kind of want to change things up. Okay, so if no such pair exists, we call this a stable matching. And Gill and Shapley showed in the 60s that for any set of preferences, no matter what list of preferences you have, there always exists stable matchings. Okay, perhaps more than one. So this is kind of the classic setting that I just mentioned, where you have these men and women. In the setting that's related to our situation, it's kind of a more modern setting. Instead of having a population of men and women, you just have one big population. We have a homogeneous population. This is our initial point process that we were talking about, the pi. Again, you have some preference orders, but let me now just focus on the thing that's related to the balloon process. So the preference order is according to distance. So you prefer every point. The way it ranks the other points is by distance. So nearer points, they prefer them. And again, we can look for a stable matching, which is defined exactly in the same way, except we have this homogeneous population. So in this paper of Howard, Paris, Pimentel, and Tram, they showed that under these three assumptions on the right, there exists a unique stable matching. Yes, so there exists a unique stable matching if the initial point process satisfies these three assumptions. And moreover, you can generate the matching, this stable matching, by a greedy algorithm. A greedy algorithm which iteratively matches mutually closest points. Okay, so what does this mean? If we have these set of points, how do I generate this stable matching that's depicted here? I find a pair of points such that each one is nearest to the other mutually, and it's not hard to convince yourself that in any stable matching, those two have to be matched to each other. And therefore, you just simply match them to each other. You know that you have no other choice, and then you kind of remove them from consideration. You throw them out, and then you continue iteratively. You find a pair of points which are mutually closest, and you match them. And this is going to generate the unique stable matching. And you see that this is exactly what the balloon process does, right? The balloon process, as the balloons grow, the first time two balloons will hit each other is when you have two mutually closest points. And when they hit each other, you pop them and you remove them from consideration and you continue. So this is exactly this process of the greedy algorithm for the stable matching. Okay, so in this paper, they studied the typical matching distance in RD. They looked at all sorts of matchings, not just the stable one, but in this talk, I just care about the stable matching. This typical matching distance is related to the density of the active balloons at time t. So here's a simple observation. The points active at time t, the centers have to be at distance at least 2t from each other, any 2 points, since the balloons are of radius t and they're disjoint. And that immediately tells you that the density of this process is at most 1 over the volume of a ball of radius t. So in RD, this is some constant over t to the d. Okay, so I won't tell you the result in the language of the typical matching distance, but in the language that's related to our balloon process, what they show is the following proposition. They show that almost surely the lim inf of RT minus 2t is at most 0. So RT over t is at most 2 in particular. Okay, and this, while they prove this in RD, the proof goes through in all of the situations that we're looking at, which is kind of an interesting thing. We have some result that works in all of the cases that we're considering, but this isn't enough to determine transience and recurrence. So transience and recurrence happens around the point 1. Okay, and indeed, it's not all of the cases are the same. Some are transient, some are recurrent. So this general result will be useful for us, but it doesn't kind of tell us if it's transient or recurrent yet. Okay, so in terms of the balloons, if you imagine what this means, it's actually telling you that the balloons reach halfway to the origin infinitely often. Okay, so if this is the origin, then you have balloons which reach kind of halfway. At time t, the distance is at most t, is less than t here. That's what it means that the lim inf is less than 2. Okay, so it's not, you don't know if the balloons reach the origin or not, they reach halfway. We've had some partial information. And the proof is a very nice idea. Perhaps for time considerations, I won't tell you exactly how it goes, but I'll just mention that it uses insertion, deletion tolerance, and ergodicity. Okay, and it doesn't use the full force of the Poisson point process. It's kind of something rather soft. So any point process which has these kind of properties would also satisfy this same conclusion. All right, so that's it for the background, and I'd like to go into the proofs a bit now. Maybe it's a good time for questions if there are any. Okay, so let's go into the proof. So let's start with recurrence in RD. Okay, so we have this picture that appeared in the first slide. So this is just the balloon process at some time at time 1 or something like this, and you also see the matchings here between the balloons that collided with each other. So you see every 2 balloons that collided with each other, who collided with who, and kind of you see the matching in the background. Okay, so let's denote by T sub x the time when the balloon centered at x popped. Okay, so if x doesn't belong to the initial point process, this is just 0. Otherwise, it's the time at which it popped. So note that this proposition on the left that we just talked about, what does it tell us here in RD? So this is just kind of a duality, just flipping this around. It's telling us that the lim sup of Tx over norm of x is at least 1/2. Right? Because if we look at the origin, and we look at a time where the distance to the center of some ball is less than 2t, this is exactly telling us that this balloon survived at least time t, but its norm is less than 2t, so it's exactly telling us that the lim sup is at least 1/2. Okay, and the recurrence happens around when the lim sup is 1. That's like the lim inf of RT over T being 1. So here's a general result now that I'll tell you about, which has nothing to do with the balloon process. Just a general result for processes indexed by ZD. If you have any stationary process, real valued, stationary process indexed by ZD, the lim sup of xn over norm of n is either 0 or infinity, almost surely. It can't be anything else. It can't be something non-trivial. Okay, so let me come back to this in a second. Let me just show how this completes the proof of recurrence in RD. Well, we already know that the lim sup of this process, Tx over norm of x, is at least 1/2. If you apply this theorem now, okay, technically you need to kind of make it indexed by ZD, so you look at a maximum on a cube, but this is just a small technical detail. It gives you that the lim sup is infinite, which translates back to in the language of RT, tells us that the lim inf of RT over T is 0. Okay, so this is telling us that not only is the origin covered by balloons infinitely often, actually you can find times where the origin is relatively close to the center of the balloon, right? As arbitrarily close to the center in a relative sense. So coming back to this theorem, I mean, just looking at it, it looks like a very classical result in probability, right? And I mean, we kind of expected that this should be known. We asked a few people. Ofer Zaytouni gave us rather quickly returned with a reference of this in the one-dimensional case. This is something in the thesis of Tanny, but the proof there relies on branching process arguments and doesn't seem to extend to higher dimensions. So it's just for one dimension. Our proof has the advantage that it's both more direct and applies in higher dimensions. Let me just give you a quick idea of how this goes. So first of all, we can assume that the process is ergodic. If we prove this for any ergodic process, that's 0 or infinite, it follows from just by ergodic decomposition. So let's suppose that the lim sup is greater than some number a. Okay, so what does this mean? Let me draw a one-dimensional picture here. Okay, so imagine that you have kind of a tree of height xn sitting at the point n. So the lim sup being greater than a means that when you stand at the origin and you kind of look at a slope a, you're going to see treetops above that slope, infinitely many treetops above that slope. And just by translation variance, that's true at any point you look at. So now if we take the treetops and we draw cones of slope A, and we look at the base of these cones. So now let me go to a two-dimensional picture looking from the top, just looking at the base of the cones. Okay, so in 2 dimensions, the base of the cones are circles or discs. Okay, so these are the base of these cones. What we would like to know is that every point is contained with, so what we know, sorry, is that every point is contained in infinitely many of these cones. And what we'd like to say is that if we increase the angle that we're looking at from slope A to 2A, if we look at more narrow cones, it's still true that every point is in infinitely many of these cones. Because I'm just trying to give you the idea here. I don't want to give all the details. Now what comes into play is Vitali's covering lemma, which tells you that you can find, these are these dark blue cones. You can find a collection of cones which are disjoint and whose 5-time blow up, say, covers everything. But this tells you that if you look at the 2 blow down, so if instead of blowing them up, you actually blow them down, right? You look at a smaller cone, then these guys, their 10-time blow up covers everything. And in particular, these smaller cones themselves cover some positive proportion of space. If their 10-time blow up covers everything, then they must cover a positive proportion. And here you see that I'm using volume doubling. So this is the first place where we see some volume argument coming into play, because Vitali covering lemma applies in all spaces, but for this consequence here, we need some volume growth, in particular volume doubling. This tells us that it's covering a positive proportion, and therefore the lim sup is with positive probability at least 2A, but the process is ergodic, and therefore it's almost surely at least 2A. So if A was positive, it has to be infinite. Okay, so this is the idea. So that's it for the RD case, for the Euclidean case. Okay, so in the time remaining, I'd like to tell you a bit about the other 2 cases. Perhaps not in as much detail because I don't have so much time. I'd like to reach the hyperbolic case, which is kind of more of interest in some sense. But actually, the proof of the hyperbolic case does go through the regular trees. So I will still spend some time on the regular trees. So regular tree, remember, we can view it either as a graph or as a continuous space. So for the balloon process, we view it as a continuous space where these points, where the balloons, their centers live on the edges, maybe look something like this. But for the proof, we'll also think of this as a graph. So let's let pi tilde t be the projection of the points to the vertices. Okay, so we just project every point to the nearest vertex. Okay, so we get a collection of vertices at time t. And this collection of vertices is kind of well separated, right? In the continuous tree, any 2 points are a distance at least 2t from each other. When you project, you maybe move them by distance half. So now any 2 points in pi tilde are at least at distance at least 2t minus 1 from each other. But also note that this process is a factor of IID. So I hope most of you are familiar with this notion. Again, I'm not going to give a definition because of time considerations, but I hope most of you are familiar with this notion. Essentially, it means that you can construct it as a function of IID variables which live on the vertices of the tree, kind of in an invariant manner. So here's a question. Given these 2 properties here, what is the maximal density of a process X satisfying these 2 properties? Okay, this is a question that we'd like to answer. So here's a trivial bound, which we already saw before when we talked about the earlier results. A trivial bound is 1 over the volume of a ball of radius t, just because the balls of radius t are disjoint, or in this case, t minus a half or something like that. So this is something of order 1 over d to the minus 1 to the power t. However, here we just use the first property, just the fact that it's well separated, 2t minus 1 separated. We didn't use the fact that it's a factor of IID. And actually, if you include this second property, this reduces the possible density by a lot. So I should also say, if you just want the first property, this trivial bound is actually more or less the correct bound. You can indeed find sets which have this density. But if you want it also to be a factor of IID, then the density decreases by a lot. Essentially, it looks like 1 over the volume of a ball of radius 2t. Okay, up to this factor of t in the numerator. Okay, so let's see how this gives the result for of transients in a tree. Yes, I should just say that this relates to previous results of Bolabash, McKay, and Raman and Virag, who looked at the case of independent sets, which is like t equals 1 on regular trees. And also, it will be important later for the hyperbolic case. So let me mention it here, that it's enough for this theorem, for this result to be true. It's enough that the factor map that we were talking about is not, it doesn't have to be equivariant to all automorphisms of the tree, but it's enough that it's equivariant to some subgroup, transitive subgroup of automorphisms. And this will be important later on. Okay, so here's the, oh yes. Okay, maybe quickly the idea of the proof of the theorem before I tell you how to use it. So you can approximate factors of IID by block factors. A block factor is just a finite range map. So you just look at a ball of radius 100, you look at the IID variables, and you only use that information to decide on the process's values. Then we use the fact that a random deregular graph converges locally to a tree. For this stronger result that I mentioned that we will need, we actually need a certain colored configuration model. We'll need to know that it converges locally to a colored version of the regular tree. This allows you to transfer the block factor map from the tree to the finite graph. So you kind of pull it back into the finite setting. And then you use combinatorial methods to bound the size of the largest 2t separated set in the finite random regular graph. So here essentially just use a union bound in the finite setting. You just compute the probability that a given set of some size is actually 2t separated. You show that if the size is large, this probability is very small, sufficiently small that you can union bound and say that it doesn't occur. Okay, so back to the balloons. How does this give us the result? Well, if we apply the theorem, it tells us that the density of this projected process, the set of vertices that we got from projecting the balloon centers, has density at most this. Applying a union bound, just taking into consideration the volume growth, which is exponential, but if you look at a ball of radius 2t, slightly less than 2t, and in fact, it's enough to look at 2t minus a large constant log t. That volume is sufficiently small that you can just union bound and get that the probability is decaying, say, like 1 over t squared. Now you apply Borel-Cantelli to see that for all integer times t, this holds almost surely. And then together with monotonicity, you get that it holds for all times t, almost surely. Or all large times t, but we have this omega here. And this tells us in particular that the limit is at least 2. Remember, we know that in very large generality, it's at most 2, so actually it equals 2. All right, so this is about the tree. And just in the few minutes that are left, I'll tell you a bit about how this works in the hyperbolic plane. So the basic idea here, we want to kind of do the same thing we did on the tree. That is, estimate the probability, the maximal density of a well-separated set, which is kind of a factor of IID, and then just use a union bound and so forth. Unfortunately, we weren't able to kind of do this directly on the hyperbolic plane. That would be an interesting thing to do, but we don't know how to do that. Instead, what we do, so as I said, this is our goal, to bound the density of pi t. Instead, what we're going to do is we're going to approximate the hyperbolic plane in this Poisson disk model by a regular tree. So you see here the regular embedding of this 3 regular tree. However, the problem is that the projection, if we take points now from the hyperbolic plane and project them to the vertices of the tree, as we did before, this has unbounded distortion, right? These points that are very close to the caps, they move a very, very large distance when you send them when you project them to the center to the vertex. So what we're going to do is we're going to remove the caps near the cusps. So you see these, we're just going to remove this area completely, all of these light regions. And we're going to just disregard points that are near the cusp. Okay, so we're only going to project these points. Points which are here, we're just going to ignore. And by doing this, we get bounded distortion. Okay, so the hyperbolic distance between 2 points is at most a constant times the distance between the vertices corresponding to them, plus some constant. And I'll tell you a bit about what this A and C are shortly. But now the proof kind of goes through in the same manner. We project the point process to the tree after ignoring the points near the cusp. Because we have this bounded distortion now, we get a set of vertices on the tree which is nicely separated. It's 2t minus c over a separated. It's also a factor of IID, albeit with slightly less equivariance. It's just equivariant to those automorphisms of the tree which came from Mobius maps, right? From isometries of the hyperbolic plane. So that's not giving us all the automorphisms of the tree, but just some subgroup. But that's okay, because as I mentioned before, the previous result works under this weaker assumption. And therefore, this theorem that I told you about before tells us that this density is at most a constant t, 2 to the minus 2t over a. This 2 is just d minus 1. D here is 3. And now we just do the same thing we did before. We use Markov's inequality plus Borel-Cantelli. This tells us that the lim inf of RT over T is at least 2 log 2 over A. This is coming from the constants appearing here. And then it just remains to say what this A is. And this is just a computation. Maybe let me come back to this. This is a hyperbolic computation. So one thing you could do, a first thing you might try to do is just take the length of one edge, right? Because as you project, you go along the edges, and then you have, like at the endpoints, you have some bounded distance plus the length along the tree. So this is a length of an edge is log 3, and this would give you a slightly worse bound. A slightly better thing you can do is take the average distance when you go 2 edge lengths. So you take this distance, and that gives you a slightly better bound. And actually, this is the optimal thing you can do with this approach. If you want to get a better constant, I guess you would need here a different approach, perhaps. Okay, so let me just end here. Perhaps here are some open problems we can discuss if you wish, but let me end here.
All right, thank you. I invite everyone to open your microphones and thank Yinon. Right. Are there questions? So perhaps I have a question, Yinon.
Yeah.
So in your proof for the tree, you show that this projection is a factor of IID. So is this the main part where it's important to be a regular tree?
Yes, I guess for this proof, yes. Although, you might try to still apply the same types of ideas. Here we used local convergence. If you have some other tree which isn't regular, but you have some nice model of finite graphs which converges locally to it, maybe you can still try to do the same type of approach. But yes, it's the factor of ID which you see in the proof came from the fact that we use just that the random regular graph converges locally to a tree, and the actual work was of bounding the size of the independent set, and the density was in the finite setting. So if you have some nice finite model which you know how to do computations there, then you immediately get it for the thing it converges to.
So for instance, if you have a tree with some sort of polynomial growth, then you would have problems in this part there.
Yes. And also if it has polynomial growth, there's a good chance that the techniques of the RD would work and tell you that it's recurrent. Yeah,
my question was a little bit motivated by Milton's question as well. So
yeah, so right. So I hope it's a bit clear now how the negative curvature helps for the transients. It's more about having this embedded regular tree inside. So it's more about the volume growth. It seems like that. Yeah. Right, so for example, one space that we don't know what to do with is the, for example, higher dimensional hyperbolic space. Right, this is because we don't know how to embed a tree there, and then you would really need to do the arguments directly on that space. And so we're not sure how to do that.
All right. So in your second item there, in the open questions, you mean you start with ZD and then you think of it as a continuum space as well, like you did in the tree, and then you project? What do you mean?
No, that's what I meant here. You could do something like that. That's what you suggested, but I meant that the underlying space is still RD, Euclidean space, but the initial point process, instead of being a Poisson point process, you start with a small perturbation of the lattice, just so it satisfies conditions 1 up to 3 that we had. So you don't want points to be at equidistant, so you can't keep them actually in ZD. You perturb them a bit so that the process is well defined. But then we lose this. I said at some point there was insertion deletion tolerance that was needed, so this is lost.
And if you just start in ZD, but then you have like extra randomness just for breaking the ties, like
yeah, there's a lot of variance to these problems. Yeah, that's a question as well. You can do things discretely and break ties. You can do things actually. I mean, there's a lot of variance you can do. You see here random growth rates, for example. The balloons don't have to grow at the same rate. If they grow at rates like between 1/10 and 10, whatever it is, the proof in RD goes through. But if it's unbounded above or below, or even one of the rates is 0, perhaps, then we don't know what to do. You can also do very weird things. You can decide that that the balloons don't grow as balls. You can decide that they grow as different shapes, maybe as random shapes. Maybe they grow like a brownie, like a brownie in motion, and when two of these hit each other, they disappear. You can do a lot of variants on these questions.
Right, thank you. Are there more questions? So if not, I suggest that we thank Yinon again. Okay.
Thank you.
Thank you very much for the lovely talk. It was really nice.
Yeah, sure. Thanks for having me.
Okay, so we continue next week. I forgot who is the speaker, but maybe Claudio can.
Martin.
Martin. Okay, good. Okay, so see you in 1 week.